Welcome to the first video in a little series about linear algebra, where I will go over the material that I will cover in my lecture for the summer school. My name is Lars Wieringa, and with that I think we can get started. So these are the topics that I will cover in the videos. First I will introduce a bit the motivation behind studying linear algebra and why it is useful. Then we will go over some elementary definitions, such as the linear system of equations, which is where linear algebra originated. And then we go over methods of solving these systems, so Gauss-Jordan reduction, and we talk about the the reduced row echelon form. Then we move on to matrix algebra, non-singularity, determinants, and then eigenvalues and eigenvectors, which are very important for engineering, as we will see later. Then we cover diagonalizability, which is in some sense related to eigenvalues and eigenvectors. And then at the end we cover an application which is important for engineering, which is systems of linear differential equations. So with that, let's get started. So, what is linear algebra? Well, there are many answers to this question, but for us today, linear algebra is the study of all of these things here. So we study We study first linear systems, and from that we go to matrices and we look at properties of matrices. This matrix, for example, is diagonalized. Then we have linear differential equations, which we can describe using matrix theory. And we look at, for example, in this case, here we have a matrix with its eigenvector with eigenvalue 3, which we will see later on. And so to look at these things, we'll just start from the basics. So we look at first at the linear system of equations. To do that, we need to define what is a linear system of equations. So let's do that. A linear system of equations is a set of equations of this form here. And so let's look a bit more at this because it's quite a big expression. So here, these a's, these are coefficients, and the x's are our variables. So if we go back here, for example, here we have a coefficient 1 and our variable x1, and we set them equal to some b's, which are here, and we take all of these in f, and f is a scalar field, so you can just think of it as a big blob of numbers, and usually it's the real numbers or the complex numbers, but we just denote it by f to keep it more general. And these indices, these i's and j's, they run through these sets with the brackets here, which are just numbers 1 up to m and 1 up to n. Right, so now we introduce some notation that will simplify this a bit. So first we collect all of those b coefficients we had before, we collect them in a vector of order m, which here we denote by b. This symbol here just means we define as, so b we define as this vector. Then we define a coefficient matrix, so that is Ra here, and we say that this is in the set f m by n, because it has m rows, so here, m rows and n columns. And now what we can do is we can say the linear system we had before, the really long set of equations, we just say this is linear equations a, b, because all we need to specify is that we need to specify our coefficient matrix and our vector with the terms on the right hand side of the equal sign. Now let's look at an example to make this a bit more concrete. So let's consider this linear system. Then we can see that b is 1, 2, as we can see here, and that a is this 2, minus 1, 6, minus 3, as you can see here. And when we would try to solve this system, what you learned in high school is also that you can subtract the equations from each other. But if we do this in this case, we get 0 is equal to minus 1, so there cannot be a solution. But we want to somehow generalize this procedure because we want to be able to solve all systems. So with that, we are motivated to look at inconsistency and at row operations. So to do that, we need to again define some things. So we say that a solution to an n by n linear system of equations is a collection of scalars, so these here, that satisfy every equation of the system. And we denote this solution as x. So this x will be something like this. So we have x1, x2, dot, 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 all the way up to xn, as you can imagine. So then we call the system that we have before, the LEAB, we call it consistent if there exists a solution, or at least one, and it is inconsistent if there's no solution. So the system we had before will be inconsistent. Then we also define the notion of an elementary row operation. So there are 3 elementary row operations. There you can interchange 2 rows. Of course, if you interchange the rows, nothing changes about the solution of the system. You can multiply a row by a non-zero scalar. Of course, if I, for example, have the equation 6x1 equals, let's say 3. If I multiply this by 100, the value of x1 will not change. I can just divide both sides by 6 and the solution will not change. So what we then have is the third elementary row operation. We have replacing a row by its sum with a multiple of another row. Showing that this does not change the solution set of the system is a bit more complicated, but you can just take it for granted. All of these operations do not change the solution set of the system. Right, so while we could have just the set of linear equations, we can also write the system more compactly in so-called augmented matrix. So what we then do is we write a matrix where we have A and B, so like this, A and B. And to make this more concrete, I will just show it in an example. So yeah, recalling the system from before, we have these two, and we place them into the augmented matrix. So we put A here and B here. And then we can perform an elementary row operation. So in this case, we add -3 times the first row to the second row. So we take this row and we multiply it by -3, and then we add it to this row. And as you can see, this gives us this row here, this one. If you write that out explicitly, you would get 0x1 plus 0x2 is equal to -1. So we get 0 is equal to -1, as we also saw before. And this means that our system is inconsistent because we cannot pick an x1 or an x2 such that every equation in the system is satisfied. Right. So with that, I think it's good to conclude the first video here. In the next video, I will go over Gauss-Jordan reduction and reduced row echelon form. These generalize some of the ideas we already saw in the video that I just finished. So yeah, thank you for watching, and see you in the next one.